Hi guys, we will derive what I believe to be the most important equation in mechanics of materials, and that is the Flexural formula.
Welcome back to the second part of the derivation of the Flexural formula. From the previous video, in part 1, we found that the strain epsilon is equal to minus y divided by r, and we called that equation 1. And there's something else you need to remember, that 1 over r is actually the value of the curvature of the beam, kappa. The units for the curvature is radians per millimeters or radians per unit length of the beam. So then we can also say kappa is equal to 1 over r, and we can rewrite the strain equation in a different form. Epsilon is equal to minus kappa y. Here we go. We have come up with another relationship between the strain curvature and a distance y from the neutral axis. We've also derived two other important concepts. One, with the radius of curvature being constant, this means that the strain is shown to vary linearly over the cross section. And two, we have also shown that at a distance y above the neutral axis, the strain has negative value because of compression or contraction. If we show a diagram of the strain to vary linearly over the cross section as we have here, we can then develop a relationship between the strain at a distance y above the neutral axis and the maximum normal strain at a distance sc. The vertical line here rotated only and does not deform, as we have previously discussed in the part 1. So from similarities of triangles, we can say epsilon, which is at a distance y, divided by minus epsilon max is equal to y divided by sc. Therefore, epsilon is equal to minus epsilon max y divided by sc. We can call that equation 2. This epsilon max actually represents some value. For example, in concrete, the maximum compressive strain is usually about 0.3% or 0.003, as shown in the Australian Concrete Code AS 3600. So from Hooke's law, we know that the stress sigma is equal to E times epsilon. Then epsilon is equal to sigma divided by E. E is the modulus of elasticity. So if we substitute the value of the strain to be sigma divided by E in equation 2, which we have worked out before, we will get sigma divided by E is equal to minus sigma max y divided by sc times E. All the E's will cancel out. Then we are left with sigma is equal to minus sigma max y divided by sc, and let us call this equation 3. What we notice is that the normal stress also varies linearly over the cross section, so the stress profile would be very similar to the strain profile. We can simply multiply every point along the strain profile by the value of E, and E is constant, to get the value of the stress. We know that the resultant force is equal to stress multiplied by area. So then the resultant force is simply the volume of this 3D stress profile. I know it can sometimes be a bit confusing. The way I visualize it is like this. The maximum depth of the stress profile, the stress profile is sigma max at the top or bottom of the beam. Okay, and the width of the stress profile is basically the width of the beam, whatever the value B is. So to work out the resultant compression force C or T, all we need to do is simply calculate the volume of this 3D stress profile. Then the internal moment would just be the force resultant multiplied by the lever arm Z dash. So we have the force resultant, which is the area of the triangle, half base times height. multiplied by sigma max. So if we take the absolute value of the maximum stress, then you can say the horizontal force, the resultant force, is equal to 0.5 SCB sigma max. Then the internal moment about z-axis would just be mz equal to 0.5 SCB sigma max multiplied by the lever arm, which is z dash. Now this solution would obviously give us the internal moment with respect to the maximum stress, distance SC, the width B, and the lever arm Z dash. However, it doesn't tell us anything about the relationship between the internal moment and the moment of inertia, I. And this is what we want. We want to figure out sigma is equal to my over I. So what do we do now? Well, first we need to take a little segment of area from the cross section and call it dA. Okay, and at a distance y from the neutral axis. Then the force on this little area would just be the stress multiplied by dA. If we take the sum of forces in the horizontal direction to equal to 0, then we can say sum of forces in the x direction equal to 0 equal to integration of stress dA. Now, to determine the total resultant force, then we need to integrate the area of the entire cross section. Note though that the resultant force is equal to 0 because there are no external axial forces applied to the system, and the neutral axis also passes through the geometrical centroid of the cross section. From equation 3, which we looked at before, sigma at a distance y is equal to minus sigma max y divided by SC. Therefore, we can say that the force resultant in the horizontal direction is equal to integration of minus sigma max y divided by SC dA. Sigma max and SC are constant, so we can take this outside the integration and rewrite the equation as rewrite the resultant force equation as minus sigma max SC integration of y dA. And guess what? The integration of y dA is called the first moment of area. So we are getting there. If we take the sum of moments about the z-axis, then it must equal the internal moment due to the applied external loads. This is a very important concept. The internal moment m is simply the resultant force, which we worked out, Fx, multiplied by the lever arm at a distance y from the neutral axis. So then m is equal to the sum of forces Fx multiplied by y. We can rewrite that m is equal to minus sigma max divided by SC integration of y multiplied by y will be y squared dA. And you've heard this before, you've seen it before. Integration of y squared dA is the second moment of area, which is the moment of inertia. We can then rewrite the moment equation to be m is equal to stress minus sigma max I divided by SC. Rearranging this, the maximum stress then becomes sigma max is equal to minus mSC divided by I. Usually, as mentioned previously, we take the absolute value of sigma max when we design section capacities. And finally, we can conclude that the stress at any distance y would be sigma is equal to minus my over I. Wow, now that took a bit of time, but I'm glad we got there at the end. So this ends the second part of the derivation of the flexural formula. If we go way back to equation 1, which is the strain is equal to minus y over r, and using Hooke's law again, we can rewrite the equation as sigma divided by E is equal to minus y divided by r. But now we also know that sigma is also equal to minus my divided by I. So after rearranging all of this, we can say that E over R is equal to M over I is equal to sigma over Y. And this is obviously taking the absolute value of this equation. If you are a structural or a mechanical engineer, then this relationship will stick with you for the rest of your entire life. I mean, even if you decide to change careers, it will somehow never depart your mind. Make sure you never forget it, because it will be very, very useful in your engineering career. We hope you enjoyed this video and found it helpful. Thank you for watching and have a great afternoon.